Hello, here's another couple of thermodynamics questions. So we're starting here by stating the term used for the energy required to change a solid into a liquid. Right, it's always nice when they just say state because we don't have to do very much. We can just say that is the latent heat of fusion. Because it's the fusion one from solid to liquid and vaporization from liquid into gas. Then for part B, define the internal energy of a system. There's quite a few sort of key terms you want to include in this when you're defining internal energy. So you want to say it's the sum, but it's the sum of the randomly distributed. That's quite often the bit that people miss out on this. So randomly distributed kinetic energies. So kinetic energies and potential energies of the, and then you want to say atoms / molecules, because we don't know exactly what we're going to get in this system, of the system. So there's a few key bits there, but try not to miss out the randomly distributed bit. Then the next part of B, there is a change in internal energy when a mass of water at 100 degrees C becomes an equal mass of vapor at 100 degrees C. So explain why. Right, so we're saying that the internal energy is the kinetic energies plus the potential energies. So the no temperature change means that we've got no kinetic energy change. So that isn't the thing that's changing. But we are getting the breaking the bonds between the atoms molecules in the liquid state, atoms / molecules in liquid state. That requires energy. In liquid state requires energy. So therefore we're getting an increase in the potential energy as the substance becomes, as water turns to gas, water turns to, or vapor or steam. You can have it whatever way you want out of all of this. So there we go. If we've got no change in the kinetic energy, but the potential energy is increased, then the internal energy has gone up. So you want to say something about those breaking of the bonds in the liquid state. Right, so now we're on to part C. The air in a greenhouse has that volume, that density, and that specific heat capacity. Immediately after sunset, the soil is transferring thermal energy to the air at a rate of 12 watts. Okay, estimate the increase in temperature of the air in the greenhouse 1 hour after sunset as a result of this energy transfer from the soil. Right, okay, so if we've got 12 watts for 1 hour, that means that we're going to have an energy transfer of our 12, because that's joules per second. So we're going to have to multiply by seconds in an hour. So our 60 times 60. So that is giving us 43200 joules. That's the energy that's been supplied. So now we go to our E equals mc delta T and say, well, rearranging that, we've got the change in temperature, E over mc, is going to be 43200 over, we've got to work out the mass then. So that's going to be 15 times 1.2, gives us the mass, because that's the volume times the density. Then multiplied by the 990, which is our specific heat capacity, which gives 2.42. So 2.4 Kelvin to two significant figures. So that was fine. Suggest two possible reasons why the actual increase in temperature of the air is likely to be much lower than the estimate. So same thing again. We want to say specifically where the energy is going from and to. So we can say some energy from the soil will go to heating the greenhouse. To go to heating greenhouse and contents. plus contents. So again, we're saying where from, the soil, where to, greenhouse and contents. So that could be one thing. We could say that there's going to be heat loss from the air through the glass to surroundings. So again, we said it's gone from the air to the surroundings. So 2 specific changes that we've got there. Right, that wasn't too bad. So I'm only doing 2 in this video because we're nearly at the end of the set, so there's not going to be much in this one, hopefully. So what we got, state what is meant by a perfectly elastic collision. So kinetic energy is conserved in the collision. In collision. Explain in terms of the behavior of molecules how a gas exerts a pressure on the walls of its container. Right, so we've got the, again, this is a chain that I've done in previous questions. So we've got many collisions with the walls, many collisions between, what they call them molecules and walls. So we can then say that the force on the molecules from the wall, is equal to delta P over delta T. So that's our Newton's second law. So we want to mention that one specifically. Then you can say that the force on wall from molecules is equal and opposite. So we want to go through that whole chain. So that's Newton's third law. So every time you've got that collision, I mean, it's probably worth actually saying on here that many collisions between the molecules and walls, that leads to a change in momentum, delta P for the molecules. Then we can say that that force on the molecules from the wall is the delta P over delta T from the second law. So we're going through this step. We've got 1, 2, 3, 4 steps that you want to put into your description. That just gets us to the force though, doesn't it? So the last part that we want to put in is we want to say that the pressure is the force divided by the area of the wall. So that 5-step process gives us that nice chain of where that gas pressure is coming from. Then we've got to explain in terms of the behavior of the molecules why the pressure of a gas in a container of constant volume increases when the temperature of the gas is increased. So we've got a greater velocity. So we can say that the velocity goes up, therefore the delta P goes up. Our change in momentum has gone up. And we've got more frequent collisions. So, and then that is going to mean that our F, because our F is delta P over delta T, and we've got delta P has gone up, delta T has gone down, therefore our F has gone up, therefore our P has gone up. So again, we've got that chain where you're just walking through these more or less the same steps as we had before, pointing at these equations, saying, right, well, delta P has increased, so F has increased, so P has increased. That's what we're doing on this step, looking at these equations in the previous description. Right, part B looks like the calculation. Whether balloon is filled with helium gas just before takeoff, the pressure inside the balloon is that, internal volume is that, the temperature inside the balloon is 20 degrees C, yep. And then all of that changes as it rises into the atmosphere. Balloon expands to a different volume, right? So this is where we can use our P1 V1 over T1 is equal to P2 V2 over T2. Now, this combination PV over T is a constant. That's what we're getting for a fixed mass. So we can then say we want to work out P2, don't we? We want to get our new pressure is what we're trying to work out here. This is our pressure inside the balloon. So we want to have P1 which is our initial pressure. So that's 105,000. That's what they've given us there. Then we've got our volume, which is 5 times 10 to the 3, because that's what they've given there. Then we need to multiply by T2, and that's at minus 30. So we're going down to a 243, converting that into Kelvin. We then need to divide by T1, which is going to be a 293 for our 20 degrees C in Kelvin. And then we've got our new volume as well, which is 1.2 times 10 to the 4. So this is going to be another calculator jobby, which is 36284, which is 36 kilopascals to 2 significant figures. Right. So yeah, it's useful. They don't use this one as much, but it is a very important and useful formula that we can use. Right, the final part suggests why it's necessary to release helium from the balloon as it continues to rise, but we don't want it to explode. Yeah, the volume increases with altitude, so we don't want it to burst. Don't want it to burst. Right, there we go. So that was 2 nice little questions. Again, emphasising the point of repetition is the key to success on a lot of these things, particularly the descriptive ones. The descriptive parts are the ones that people really fall down on. They miss things out. They don't have these nice chain arguments like we had here in A part 2, which then leads on to A part 3. So it may end up getting a bit dull repeating these things, but it really is worth repeating them. That's how you cement it in your mind. So that's the end of this video.